Okay, thank you. Then I jump to the talk. So here is a brief overview. I'll try to go through everything, except possibly the compositional linking there for with the interface. But I'm very eager to show you that slide because it's with special example, which is pattern example, simple, but to demonstrate the entire theory. So I'll try to give you an impression about the theory. And here on this slide, I overview it. So actually the origins of this theory is the original version is by Yanis Mouskovakis, and I have been developing it for some time. And there is even prehistory of all this theory, but now I focus on it. What it is about here, before going to its syntax and semantics, is this. So Yanis developed a special formal language, actually classes of formal languages for the recursion theory. So recursion theory in general is not a language, but it's a mathematical structure of functions. So one starts with some simple functions, some simple constants, and uses the operation of composition and the operator of recursion, and can build up all primitively recursive functions. And then if we add the mu operator, which is a restrictor, then we get also the partial functions. And so to say, all the mathematical structure of the entire hierarchy of the functions. And that is an alternative to the mathematical models of algorithms. Classically, it's an alternative of Turing machines and lambda calculus, by the way. So now here, in these classes of languages, Mouskovakis introduces a formal language with a special formal constant that designates the recursor operator, and I introduce something for the mu operator, I'll show. And at first he introduced it for untyped system of recursive functions in untyped languages. And then in 2006, maybe he saw me that I was struggling with some things in situation theory, the mathematical theory. Also, like in the recursion theory, because my original expertise is in recursion theory and automata theory, formal languages. So he probably saw me that I was struggling only with the mathematical structures of situation theory and information, simply like a mathematical structure of the functions, and he came up with a formal language of recursion theory. And he published a simply typed theory with examples for computational semantics of natural language. And already for more than 10 years, I have been working on these two versions, simply typed systems for the recursion theory. And I'll tell you what's the difference. And again, my idea is directly to be used for computational semantics, actually for algorithmic semantics of processing natural languages, more specifically for syntax semantics and for semantics of natural languages. And this is a very much open area. Computational syntax is done everything. There are large, very sophisticated, large-scale grammars of natural language for the syntax, but the semantics is the nightmare. And it's extraordinarily pleasant. It is my obsession. So this is the purpose, primarily for semantics of natural languages. But it takes the ideas of semantics of programming languages. So everything that is going to show you is actually coming from procedural semantics of programming languages. And I'll show you even one more subtle thing than just for programming languages. So the idea is such, natural language syntax the syntactical structures of the expressions there, let's say sentences, we get them translated into this type theory of recursion. For the natural language, acyclic recursion, Muskwaki says it's enough, but it's not enough. I'll show you why and where. And then we know from all formal languages of logic systems that the formal expressions, they get denotations by structure of the terms that we define. We use well-defined terms, and we assign to them semantical denotations. So this is from the first and second items there, directly to the denotations. In this type theory, instead of jumping directly to the denotations, which is available, of course, one can mix up these algorithms and jump, and that is actually by any standard simply typed lambda calculus, although some people add procedural semantics. But here the procedural semantics is more than just procedural semantics. So there is a special system which defines algorithms step by step, smallest possible steps, or you can define, you use set sequences of smaller steps, and you define them as a big, large jump, several steps in the classical ways. So there is a way to define formally algorithms, which means that to define formally recursive, usually recursive systems for defining recursively functions, which are denotations. And why functions? Because this is in this entire system here, by Muskwaki introduced it, is by Koenig with the encoding. The relations, they get encoded by characteristic functions. The characteristic functions, they get encoded by functions from functions to functions, etc. So this is the picture of the first row. So how does this algorithm, the denotations are by standard structure of the terms. How are the algorithms defined there? So the system, all this formal language comes with a system of reductions, which means reduction calculus. And each term, well-formed term, can be reduced to a special canonical form. So there's special theoretical results, and here I overview them. So there is a special theorem that for every term in this well-formed term, of course, effectively, the reduction calculus reduces it to its canonical form. And then this canonical form, I'll show you what it is. This canonical form defines a couple of functions that are defined by mutual recursion in the simplest possible ways. One starts with the simple functions and recursively by mutual recursion, of course, more interestingly, defines them. And the other algorithmic semantics, also there is a big theorem. This theorem shows that for every algorithmically meaningful term, which because there are some so simple terms that do not designate any algorithm, they just denote whatever they denote directly with 0 steps by the variable valuation function. So for every algorithmically meaningful term in this type theory, this canonical form determines the algorithm for computing the denotation of A. So the canonical form of A actually can be considered as the algorithm in syntactical way. This is it. So I myself am working on this picture, extending and fixing various things that Muskwaki introduced. I fix them in the way I know they are useful for computational semantics, and extend the reduction calculus, and also the entire type system, I extend it with various operators. So here is the type system. It's simply type theory, but it has this special blue S. It has a special, specially designated type for states. for in the programming language, the states that can be the memory states in the computer where it arrived. But for natural language, these are the states that designate the simplest possible elements of a context. This is extraordinarily important for AI. A robot, in order to pick up garbage and trash it, the robot has to know where this trash is, the location, space-time location, and at what time, and where to. So this is the simplest possible context or state. So then there is a typed vocabulary. The type vocabulary consists of constants and variables. So here I put the constants as infinite enumerable set, but for decidability, one better takes a finite number of constants, and even with a finite number of constants, by inheritance from type lambda calculus, decidability can be tricky. And here it's open problem. I haven't even touched it yet because I'm still working on the reduction calculus. So the logical operators, I introduced them as logical constants of special types. Not like in first order logic, extra thing categorematically. Here they are special constants of special types, and they have special denotations. The important thing, the difference from the standard lambda calculi is this red 3D, E, and F, that the variables in any type, the variables, they are not only typed, but we divide them into two kinds. The pure variables are the ones that we know. So in the pure variables, we abstract by lambda or quantify by the logical quantifiers exist for all. And the recursion variables, or I call them memory variables, are the important ones. So they are a significant part of programming languages and of computer processing. These are variables, and they are actually called variables in computer science. They designate memory locations where we save information. Quite often, for example, in Java, those are pointers to memory spaces. So here there are special variables of all types. So this is the vocabulary, and this is the syntax. The entire, I tried to put it on one slide. So the first line, 3a, is lambda calculi, lambda calculus, or lambda calculi of any standard way. So the second line, recursion term, this is the innovative thing that has been introduced by Moskovakis. So actually, this in the curly brace, the entire row in the red 3b is one term. There is a head term, and then in the curly braces, this is a system of assignments. So this system looks like, and many people just, oh, okay, I ignore this because these are Let expressions. This is generalization, algorithmic generalization of the Let expressions. So I have published already a proof, a theorem, a proof that proves that this is not algorithmically equivalent to Let expressions. Of course, they're denotationally equivalent. So this is actually a term that designates recursively defined function A0, denoted by A0, and the recursively defined function A0 actually depends on a system of mutually recursive functions that are defined inside of the curly braces. So then the logical operators, so here directly sees that they are actually constants. There is a very important reason why I decided to define them in this way as constants. Of course, they're logical constants. And pure quantifiers, I call them pure quantifiers because they are also generalized quantifiers. And in this talk, I'm not showing anything about any of these quantifiers except one. So 3 C, D, and E, and F, G, and H, all these are defined by myself. So very importantly, F, this such that is a restrictor, and actually it's a generalization, but equivalent to it by a numerical encodings of the mu operator in recursion theory, where the mu operator is the smallest number x such that a of x. And it actually pushes the functions, the class of the functions, or the relations by currying above the total functions, because this, the smallest, may exist after certain point where the function is not defined and one can never reach it. So here it's a generalization of that mu operator, and G and H, actually these two operators, the first talk in the afternoon, so the speaker said knowledge, beliefs, statements, these are very important, especially for the language of mathematics, but now I'm not going to talk about them. So these two operators, they introduce scope of statements. Theorem T proves that and that statement. So this that and that statement may depend on information saved that in the memory that is external to the statement and is to the prover or to the one who reads the theorem, or it can be the scope of the theorem itself. So these two introduce various and actually ambiguities, and that's the purpose of these two operators. So here, the talk, I'm not showing any of those 10 plus reduction rules, but those reduction rules, as I told you, they reduce every term to its canonical form. And the rules, the reduction rules, they are defined in such a way that they introduce chain copying information from one location of the computer to another. And this blows up exponentially as many times as, especially there is a rule which is application rule, then you get piled up this chain, copy information from one location to another, and they exist there. They can be also generated in natural language processing when you put together compositionally the terms of the parts together into the term of the sentence. So the sentence, it consists of subject and verb phrase, and they have terms, the subject and the verb phrase, and you put them together compositionally, and then you copy them from one memory to another. Instead of that, we simply squeeze these two assignments into one. I have even more generalized rule, but I'm skipping it. So actually, it reminds you here for the eta reduction, but it's more complicated, although it looks it's a very simple rule. So that's it. So now, this is the example. I'll come back to it if I have time. How much time do I have, Sandra? You give me more time because I started quite later. Because I would love to return to the example. And then probably, I don't know, but I would like to come back. So here is the general, the conclusive, the general picture of all of that, although I haven't shown you more details. I gave you the formal syntax. I explained to you the semantics, actually, without showing the full definition of the formal definition of the algorithmic semantics. I didn't show you the denotational semantics, so you have to imagine them, or just go and read whatever I wrote and ignore the typos. So here is the motivation for my work here. So one important thing here is that it is also on the table for research for the parametric programs. So free variables in programs, they have to be instantiated somehow, either when you call the function, the program, or during the execution, or somehow. So here, for me, the parameters are extraordinarily important in natural language because of the ambiguities. And scope ambiguities are tremendous in all of the varieties. So that is what has been preventing computational semantics to enter formally the logical approaches, so-called symbolic approaches into the NLP in AI. But I stay in that direction, and I'm firmly convinced that, and the world is also convinced, especially in recent years, that logical approaches cannot be avoided in for robots and for AI. So here, parameters I call not pure variables, pure free variables, but the free location variables. So with a term, recursive term, one can have bound memory variables, recursion memorials, and they're bound by the assignments, but one can have also free occurrences of parameters, the recursion of memory locations. And I'll show you with the example that can be instantiated. And this is extraordinarily important for natural language to cope with a huge amount of language instantiations in classes of instantiations and in parametric algorithms. And these parametric algorithms, recursive terms, they can be instantiated later when the context brings more information. So then translations between natural language in everyday, and that's a huge task. People, and we settle down with domain-restricted natural language fragments, because otherwise it's a tremendous task, and we don't abandon that tremendous task. But for proofs, mathematical proofs from natural language of mathematics, that's a very important task, and I cherish this task, and that's my motivation. Because actually then we get, if one manages to translate from natural language of mathematics to formal languages of those provers and verification systems, then it's very pleasant to translate from mathematical language proofs written in the, so to say, precise language of mathematicians, but still natural language, into the formal language of proof systems and of verification systems, and vice versa. If a prover proves a theorem, to translate it back into natural language for ordinary people to read. Okay? So now here is, I have already started this task, the currying versions to be inserted, to be extended to explicitly relational type theory without currying, because the partial relations, not all partial relations can be encoded with curry. That's a classical, there is a classical proof that partial relations are more than currying can grasp. So this is actually in my 100 years ago, I say, in my dissertation, PhD dissertation, which I defended in Russia, but I wrote it in Oslo. So what I did, Barwise introduced very pleasant system in philosophical way, situation theory, situation semantics, in very informal but very precise way, with very valuable ideas. And I made the mathematics, and I made the same thing like in recursion theory, because that was what I knew. I made it without language, just as a mathematical system of structures of recursively defined situated objects. When I arrived after years in Stockholm, in the logic group of Uppsala, Stockholm, I realized that there is something called dependent type theory. And actually what I did was dependent type theory, but I did not know to use the word dependent because it was recursively defined that the recursion is about dependent objects. So nowadays I use the well-known term. And now I'm back to reviewing all this by Moskovakis' machinery to make it with formal language. So this is my motivation. If I have time to show you an example. Okay, I show the example. It is because here is the example. So again, it's a small sentence in natural language mathematics. And the sentence is the cube is large. So this is a very common pattern. You expand this, the noun phrase, the cube, with all sorts of things. And is large, you can replace it with a very complex verbal phrase, and the pattern is still the same. So the cube, its canonical form is 5b and c. This is one term. So why I have separated c in the memory c, we save the value, the function cube. Cube is a function from objects to truth values. For those objects, it's true for those objects that are really cube in a given state, and false for those that are not cubes, and an error for those objects that are not known what they are. They are not appropriate to be cube. False or, so they don't have the value true or false. So this is allowed in this system, errors. So why I have separated? If I delete this, the red one, I get underspecified term. D is specified. This is the definite descriptor D. And C is a parameter. You can put there instead of cube, you can put a man, you can put a cat, dog, you can put a dodecahedron, any object that is eligible to be large or not to be large, otherwise it's going to be error. So actually 5b is a parametric algorithm, where C is a parameter. And in this way, this recursion term is simple and it grasps a full class of denotations with this special algorithm, and see if it's complex term, the algorithm will be more interesting and more complex. So is large here is also, I made it as if it looks like a constant of type of the properties of entities. E is for entities, T is for truth values. So is large is denotes, you can think about it as a constant, denotes a property of entities. And then the sentence, the cube, I can go step by step in a Montegovian way, a recursive nested term, and decompose it by using the reduction calculus. If the sentence is more complicated, then that will involve a lot of steps. But the system allows me, if I define recursively the notion of a canonical form without going through the reduction calculus in a specific way, I can immediately, from the parts of the expressions, from the canonical forms of the parts, I can get immediately the canonical form of the more complex expressions. So actually, T2 is this directly the canonical form, or otherwise T is large applied to T0. I go step by step and reduce it by using the reduction calculus. And 6C applies the chain rule, so I get rid of E gets assigned to whatever is it E. I don't need to do that. I directly use I instead of C by this chain rule, and I get immediately the canonical form. So this is a simple baby example to show the entire system of reductions without the rules. So you don't see them, but you have to look them in the papers.